So let me next turn to open problems in the quantum realm. Earlier I had a list of problems that physicists would consider to be open problems in theoretical physics. Most of these problems, and those that list that I provided earlier, I do actually go into a little bit of detail about what those various problems are. But ultimately the most important question is there a theory, a unified theory that unites both general relativity and quantum mechanics into a single unified theory of quantum gravity? Now, even this problem, the other problems mostly do not give rise to problems in open problems in mathematical physics, and this problem in itself, the problem of quantum gravity, doesn't necessarily give rise to a mathematical problem, but it does give rise to a number of questions which probably do fall under the umbrella of open problems in mathematical physics. I'm just going to talk about one or two. There is a space-time, a classical space-time, like a solution of GR, which in 4 dimensions is a unique maximally symmetric Lorentz manifold with a constant negative curvature, scalar curvature. Namely, it has a negative cosmological constant, and it's the only matter field in the model. These space-times arise and are of interest from many aspects of quantum gravity. I've mentioned one or two here, but these problems, these space-times, crop up in a number of very interesting situations. Now, anti-de Sitter space is just a classical solution of general relativity. So we can talk about its stability in very much the same sense that we can talk about stability of other solutions of GR. The difference here being is this particular space-time is of particular interest in quantum gravity. Certainly within the area where it's been motivated, we would hope that this space-time was stable. So there's motivation for studying these spacetimes. Now there are 3 maximally symmetric spacetimes. There's the Minkowski space, vacuum, the case lambda is equal to 0, positive lambda, which is called de Sitter space, and both Minkowski and de Sitter spaces have been proven to be stable, at least linearly stable, a long time ago. It turns out that the ADS spacetime is a harder nut to crack, but it's turned out recently there's some evidence that it's not stable. It's actually been shown by a combination of some analytical results and numerical results that ADS appears to be unstable to small perturbations. Now the problem is, of course, is that these examples that show it's unstable don't prove stable unstable in general situations. And of course the examples are very special because the problem's difficult. For example, it's spherically symmetric systems have been studied and found to be unstable. So the aim to prove stability in a more general context is very challenging. So the ultimate goal is to prove or disprove the stability of anti-de Sitter, or at least in the first instance to determine whether it's non-linearly unstable to general nonlinear perturbations. In particular, in the case that people have studied, the special cases, there is, in which they do find an instability, there's a very interesting phenomena that occurs describing how the instabilities occur. There's a mechanism which is reminiscent of turbulence that causes the instabilities to develop, and certainly not the whole space is unstable, but certain regions are. So the question is there some evidence for very simple situations that the ADS spacetime is unstable, but certainly no general results. So the problem would be to prove some general results about stability, and this is a very, very hot topic in mathematical analysis. In many theories of many ideas in quantum gravity, the universe is supposed to be higher dimensions. So in general relativity, the universe is supposedly 4 dimensions. Within quantum gravity, we may be looking at high dimensional space-time, which means that it may be of interest to revisit old questions in 4 dimensions to higher dimensions. For example, the uniqueness and stability of higher dimensional black holes is of current interest, generalizing any theorems that we had in 4D to higher dimensions. This is also a topical subject. I won't say anything about that. Another problem that arises is question of quantum resolution of quantum singularities. Now, the Hawking-Penrose theorem says that generically singularities arise in general relativity. Now, if we go to a full quantum theory of gravity, do those singularities persist, or are they resolved? Now, there are 2 popular approaches to quantum gravity. One is something called loop quantum gravity, which is kind of like an approach based on 4D general relativity and geometry, and string theory, which is perhaps more based on a particle physics approach. So the question of black hole singularity resolution and cosmological singularity resolution has been addressed. There are claims, at least for very simple spacetimes, i.e. They have symmetries and perhaps there's no inner homogeneities, that the singularity is resolved. So in this case, these theorems need to be generalized to more physical situations. On the other hand, in string theory, although some singularities are resolved, not all of them are. So the question is a little less clear in string theory. So this is an area of ongoing research. Can you resolve singularities within quantum gravity? This just mentions that the way that, for example, the singularity is resolved in cosmological models for loop quantum gravity is, instead of having a singularity, the model evolves through a bounce. And so these non-singular bounce models have become quite popular in cosmology. Many of the problems in this area are probably not problems in mathematical physics. However, I've pulled out a couple that may be potentially regarded as problems in mathematical physics, or they will be. For example, once a fully consistent theory of quantum gravity is developed, there will be questions about its well-posedness, about its structure, and so on. Certainly, the question I just referred to, the singularity resolution, is a problem in mathematical physics. And there's also another problem called black hole information paradox. And this is a very popular topical problem, although I'm not entirely sure I would regard it as a problem in mathematical physics. It's this problem here. This is the qualitative description of the problem. Let me just sort of go below and discuss it a tiny bit more technically. Here's the deal. In general relativity, a black hole is formed by the gravitational collapse of a body. That is, general relativity predicts the formation of a black hole. This is a classical process. When one looks at how, after the black hole has been resolved, let's say we have has been formed, we might have a Schwarzschild solution with an event horizon. Then if you take into consideration quantum effects, quantum particle creation effects, then it turns out that these black holes emit something called Hawking radiation. That is, the event horizon is not a one-way membrane. There is some information that escapes across the horizon to infinity, and this is a quantum effect. Semi-classical arguments means we're not working with full quantum gravity, but some perturbation of general relativity with some appropriate constraints. Now, if this procedure continues, what happens is, as the radiation, which is thermal, which means it's statistical, doesn't have any information associated with it, as this information escapes, the black hole mass reduces, and eventually what will happen is the black hole will disappear. But within semi-classical arguments, quantum arguments, semi-classical quantum gravity, there's no reason why any of the information should be lost. So what we have, the situation is, we have a black hole that's formed with all sorts of information. The radiation is emitted thermally, so no information is lost, and if the black hole disappears, where has the information gone? This is the so-called black hole information paradox. And it's a violation, if it does occur, it's a violation of the second law of physics, thermodynamics, and poses a problem. Now, there are various, so this is a very topical problem that interests people in theoretical physics. Suffice it to say here, I'll just mention a couple of things. There are a number of ways around it. Most importantly, either the semi-classical approach does not capture the full physical picture, and then if you look at this within a full quantum gravity theory, the picture might be quite different. Secondly, perhaps instead of the black hole disappearing, it reaches a minimum mass and then explodes, and the information goes to infinity. And there are some other possibilities. So this is probably not a problem in mathematical physics, but pretty close to being so. If we had a better described theory, we could actually attempt to answer this in a mathematical fashion.